In this lecture, we're going to discuss feature engineering for CyberAI, or more specifically, feature engineering for intrusion detection systems, or IDS. We're going to transform how to transform that raw security telemetry, that data, the logs, and so on, so network flows, endpoint events, DNS records, all of those things into high-quality features that help machine learning models detect attacks and reduce our effort as analysts. The core message that you can carry through every step here is that model accuracy, what we eventually build for AI, begins with the data itself. Even a state-of-the-art algorithm can only learn what your data makes visible, what your features make visible. So if important behaviors are hidden or if they're inconsistent or noisy, your results will underwhelm no matter how fancy the model that you make. We're going to work from principles here. We'll define what a feature is in an IDX context and survey some common telemetry sources and look at a toolkit that we might use for this. So parsing, normalization, encoding, and so on. And we'll compare multiple strategies for feature selection and dimensionality reduction and call out where each helps. So let's begin by looking at a definition of a feature. You can think of a feature like a column in a spreadsheet. It contains a certain type of information. We have rows and columns in spreadsheets. We might store a person's height. That would be a feature in a more generic context, not necessarily related to cybersecurity. And their weight would also be a feature. Each of those would be a column in the spreadsheet, and then each row of that spreadsheet would represent a different person, and then have a different value for each of those columns or features. In intrusion detection, a feature is any measurable property that we can compute from telemetry. That's a mouthful, isn't it? Think about a feature as being something that we can measure that we might get from a log file. Now, we might get that information directly from a log file, or we might compute it from that log file. We might encode that behavior, say the number of failed logins in a minute. We might count those up, and then that becomes a piece of information, a piece of telemetry that we have. The target is the label that we hope to predict. So what are we trying to predict with that telemetry that we're capturing? So maybe an attack versus a normal flag. We're trying to capture that behavior and determine if it's an attack or just simply normal traffic that's happening on our network. And we keep asking, we come back and we ask, what information do we need in order to make things visible on our network? What behavior do we want to make visible? What data then reliably contains that signal? In the instance of failed logins, we're able to look at a log file and determine this account has a certain number of failed logins and be able to count that up. And we can compute that quickly. How do we do that? How do we compute it quickly and consistently? Of course, we need to be able to compute that before we're able to predict, or before we're able to use that to predict it. Even if we were dealing with this outside of an AI context, when is that threshold? What's that threshold for failed logins? Is it 3? Is it 5 within a minute? Where's that threshold? We have to determine that initially and maybe set that threshold. But as we feed more and more data into AI, or that model that we're building might determine for us, hey, when it gets to 7 in a minute, that's when it's indicative of an attack. Or maybe that number is 5. Maybe that number is 3. What is indicative of an actual attack? And that's what we're trying to get towards, so we don't have to determine what that number is, what that threshold is. We can simply rely on the model that we're building to help us find that number. So let's anchor this in 4 high-leverage telemetry families. First, network flows, a net flow or an IP fix, or something like that summarizes the conversation in terms of bytes, packets, duration, ports, protocols, TCP flag counts, those types of things. And flows are compact, they're ubiquitous, they're ideal for modeling volumetric or structural behaviors like scans, data exfiltration. They can help us alert to that, or beaconing. Another piece of information that we might get, application layer metadata, DNS queries and responses. HTTP methods are interesting. The HTTP status codes or the patterns for the headers, TLS fields, and so on. Those can all help us to find the intent without actually needing to inspect the payloads. We don't have to look deep into those packets in order to find those things out. That's especially important when encryption is in play or when privacy constraints limit our ability to inspect that content. Another method is authentication and identity logs, so identity provider events, VPN concentrator logs, authentication entries from an operating system. Those are great for detecting password spray attacks and possible travel, privilege misuse, and so on. Session hijacking you'd find with that. Another one then finally is endpoint events. We might be able to look at the starts and the command lines and the parent-child relations, file modification times, driver loads, those types of things. We can find all of that from an endpoint event. And you don't need every source for every problem. The idea is to choose the smallest set that exposes the behaviors. That reduces the signal to noise, or helps with the signal to noise ratio, because we have higher signal and less noise in that case. And we're able to then process the data consistently and efficiently as well. Feature design depends on the shape of the problem. If your goal is just simply attack or not, yes, no, well, then your bias is going to feature toward separating malicious and normal populations. If your goal is multi-class categorization, say distinguishing phishing from brute force from port scans, so slightly more nuanced than just simply attack or not attack, then we have to find some features that encode the class-specific signatures. We have to find features that help us determine what that attack looks like. Next, then, we distinguish point anomalies from behavioral patterns. A point anomaly might be a single flow with an extreme number of bytes out, an extreme number of bytes outbound. Could also be a behavioral pattern, might be a reporting beacon, something that's happening every 5 minutes, has low data, but it's highly regular. The former might need robust scaling. It might need outlier-sensitive features that we find, while the latter demands time window aggregates and some other metrics based on the time period. Operationally, real-time versus batch matters. Real-time pipelines require features that can be computed with tight latency budgets. We can compute those easily without using a lot of resources to do so. Batch pipelines, though, allow us to look at aggregation more and look at temporal context as well, time-based context as well. Finally, labels. If you have reliable labels, you can evaluate feature utility directly and consider supervised selection methods. Look at what data you have manually. If labels are scarce, well, then you can lean on some unsupervised techniques to try to find where those clusters lie. Domain knowledge, of course, helps here as well when you're trying to build a large language model. When we're working with feature engineering, we typically treat it as a pipeline, a sequence of deterministic steps that transform our raw inputs into a table that's model ready. Each step has clearly defined inputs and outputs and can be tested in isolation. For example, when we parse something, we normalize the timestamps. If we parse that log file, maybe we join whatever it is with our asset inventory and we encode categories and we add some scaling. Those types of things, we can repeat that over and over and over again because the log file should look the same from day to day. Obviously, the entries will be different, but the format will be the same from day to day. We can then unit test that feature code, write some small tests that expect certain behavior. So that timestamp normalization is a great example. Make sure that that can handle different time zones. IP parsing, making sure you're rejecting things that are not IPs or at least placing them somewhere else so that way they can be manually examined. The IP address if it doesn't make it through your pipeline. The idea is to keep code stateless so that way we can rerun that code without needing to know or needing input from a previous step directly. We don't have to hope for the best. When we kick off our pipeline, we'll have some outputs and we can restart that pipeline from, say, step 3 if something fails in step 3, or in step 4 downstream. We don't have to rely on that pipeline to work from end to end every single time. Obviously, we want to use version control and can keep those configurations versions so we can always revert if something changes or if we mess something up. The idea is to have the same input produce the same data set over and over and over again. We can produce the same data based on the same input. That helps to lead towards that abstraction and repeatability and reproducibility that we want to have when we're talking about building an AI pipeline. When we want to normalize timestamps and fields, there are many different ways to get at that. It helps to cut down chaos within our log files and within all of the telemetry that we collect. ISO 8601 helps us to define timestamps, and that is a standard that we can use then to provide that timestamp and to enforce that timestamp across our entire organization. We can also standardize network fields, agree on the naming, source_IP, maybe source_port. And everywhere we have a source IP or a source port, we name those the same things across our entire organization. That helps to unify everything across all of our sources. And if we have different data types that are coming in, maybe a port is being stored as a float somewhere or an integer somewhere else, we can canonicalize that and say we're always going to store source port as an integer because we know that it'll be between 0 and 65535, and we can always store that as the same thing. That normalization step, it's not glamorous at all, but it helps determine whether downstream features are going to be clean or not. One of the things we run into when we're working with data is missing data. That is really inevitable. So we can start by profiling each column, look for the number of missing distinct data, look for the number of missing data points within each column. You can just get a count of that, where a certain column is null or where a certain value is null or is empty. Programmatically, we can do that. We can do that with an SQL statement. Be aware of empty versus null and make sure that you're capturing both or looking for both. And maybe look for systematic patterns. Are things missing only on weekends? Are they missing for a specific device type? Are they missing after a software update? Those patterns help to signal the collection issues that we might need to fix upstream. For each feature, we can choose a policy. We can choose if something's missing, do we drop that row? Do we impute a value? In other words, do we make up a value based on the average or something like that? Or do we just keep the missingness as a signal? Do we keep that missing value, leave it as missing because that might signal something important in a cybersecurity context? Dropping is always acceptable. Well, not always, but it's a lot of times acceptable if that loss is small and random. If we want to impute a value, we maybe want to make that constant. If 0 means 0 traffic, or if we do a median or a rolling mean or something like that, might be useful within the context of whatever data that we're missing. And we can also, and as another strategy, create an explicit flag. So is missing IP or something like that, is missing, and set that to true false within our data. Then we know that, yes, this was missing from this data, when we're not going to try to hide the fact that it's missing by imputing a value or by deleting the row. We're just going to acknowledge that it was missing because maybe that information is important later. Categorical variables such as protocol names, HTTP methods, countries, device roles need encoding. For fields that are low cardinality, one-hot encoding is simple and robust. Each category becomes a separate 0 or 1 column. It's easy to determine that, it's easy to interpret, it's safe from leakage, and so on. But if the field is high cardinality, like domains or user agents, that can pose a challenge. One-hot would explode feature count. Options like hashing tricks we might include there help to map categories to a fixed number of bins and constrain that dimensionality. We can also use learned embeddings if we have deep models and adequate data. But hashing is fast, it's stateless, sometimes introduces collisions for when there's enough data or significant amount of data. Target encoding replaces each category with average target rate for that category. It can be very predictive, but it's dangerously prone to leakage if computed on the full data set. If you use it, compute with cross-validation folds and use smoothing to avoid overfitting rare categories. Finally, stabilize vocabularies. Build encoders on the training set, persist them, and apply exactly the same mapping to validation and test sets. Unknown categories at inference time should map to an other bin rather than crashing the pipeline. Let's talk then about scaling and robustness of our pipeline. Scaling is essential when the downstream model cares about distances or margins. If you're thinking k-means or SVMs, neural networks, that's appropriate here. Security telemetry is heavily tailed. Bytes out, connections per minute, fail logins can span orders of magnitude. So robust scalars using medians and interquartile ranges reduce sensitivity to those extreme outliers that we run into with security telemetry. For strictly positive counts, log transforms can compress dynamic range and reveal structure that the model can then learn from. The idea is to fit scalars on the training set only and persist parameters. Apply a scalar fit on combined training plus test leak information. Treat scaling as deterministic within the pipeline with its own tests. Let's talk then about temporal features in Windows. Attacks unfold over time. That's that temporal factor. We need features that summarize behaviors across those time windows. Choosing fixed windows that are tied to operational rhythms, maybe say 1, 5, and 60 minutes, those are common. And within each, you compute the rolling statistics, the counts of number of connections, the mean and standard deviation of bytes out, min and max packet sizes, number of distinct destinations, unique countries. Those types of things are definitely helpful to calculate and to record during those time windows. Exponential decay features weight recent events more than older ones. That captures momentum. Is an attack beginning? So an exponentially weighted moving average of failed logins highlights a surge without waiting for that full window to happen. And causality is non-negotiable. When computing a feature for time, include only events at or before that time. When you shift windows or compute rolling stats, verify no look-ahead slips in. In evaluation, use time-aware splits so the model simulates real deployment. Train on the past, validate the near past, and test on the future. At the flow level, start with the basics, bytes and packets in each direction. Flow duration, bytes per packet, packets per second. Directionality matters. The ratio of outbound to inbound bytes can differentiate exfiltration requests from simple requests. TCP flag counts carry semantics. A preponderance of SYN packets without corresponding ACKs suggests scanning. Repeated resets, or RSTs, can indicate failed connections, or resets triggered by active defense. So compute those counts and ratios of SYN, ACK, reset, and FIN attacks within the TCP flags, and you can compute those per flow or per window, per time window. Fan out and fan in metrics summarize how many unique destinations a source contacts and how many source targets a destination has within a window. Port scan produces high fan out with low bytes. Distributed denial of service, or a DDoS, would have high fan in towards a single destination. These simple interpretable features often outperform exotic constructs because they map directly to human reasoning about traffic. Let's look then at DNS. Everything is DNS. You might have heard me say that in class at some point if we've had a network class or another security class together. Everything comes back to DNS. DNS metadata exposes campaign mechanics without payload inspection. Domain name structure features, total length of the domain, number of labels, average label length, character entropy. All those help identify algorithmically generated domains. Record type distributions also reveal unusual use like TXT records and exfiltration, and NX domain rates, so no domain found, no DNS name found. The fraction of non-existent domain responses, a spike could be indicate something is wrong with lookups or malware, misconfigured malware. TTL values, or time to live values, And their variability tells stories too. Very low TTLs and many unique IPs per domain suggest some fast flux hosting, lots of changes in the hosting for that domain name. You can also track newly seen domains per host and bucket domain age using registration dates if that's available. Freshly registered domains are often riskier, especially when contacted by multiple hosts shortly after registration. So considering that as a data point, and we talked a little bit about that in a previous lecture. You can combine per query features with rolling aggregates per host and per domain. Single odd query really isn't much typically, but a burst of high entropy domains with an X domain and short TTLs across several hosts is quite a significant signal. From HTTP logs, we can extract request methods, status code distributions, response size statistics, those types of things. If we have abnormal mixes, many post types of methods with small bodies, unusual paths, it can indicate staging or maybe a command channel or maybe some type of scanning for a zero-day type of exploit. User agent strings can be informative at times. Remember, user agent strings are highly suspect as data points because they can be programmatically changed or changed trivially for requests, but we can sometimes use those as precursor indicators. Odd refers, the refer log, refer header might be also used as a signal. TLS metadata further helps to sharpen the features without actually needing to decrypt anything within that TLS stream. Tracking protocol versions, cipher suites, deprecated versions, weak ciphers can all help to correlate with shady or older toolkits. The server name indication, or SNI, reveals requested host names, and we can do the same thing that we would apply structural features that we use for DNS. Those types of things can be gleaned from SNI data on what would otherwise be encrypted traffic. As always, compute per event fields rolling aggregates. That's useful here as well. Rarity and reuse patterns are powerful. A certificate issue that suddenly appears across dozens of new destinations contacted by only a handful of hosts could be an early warning. Identity features model how legitimate users behave, track failed success to login to fail login ratios, user and device tracking across Windows, where do people log in, what times they log in, and so on. Geo and time anomalies are pretty straightforward, but they're really effective. Computing distances and travel time. So if I try to log in today from Stevens Point and then within an hour try to log in from London, well, chances are that I'm not in both places at once. Now, I could be using a VPN, of course, but chances are that's at least a signal that something is going on. If suddenly I have 5 failed logins from London and I had a successful one from Stevens Point an hour ago, then something's definitely going on that we would want to look at. Adding multi-factor authentication adds some depth. We can have the number of prompts that happen, the number of outcomes, was it successful? We can be tracking sequences for MFA and so on. And finally, endpoint execution. That endpoint telemetry exposes execution behaviors for us. We can build features with parent-child relationships. So spawning PowerShell or Office, we suddenly have a script on here that's spawning Office script interpreters, those types of things. Why is that happening? Do we normally have that happen on this machine? That's a behavior that we can then use and monitor to ensure that it's non-malicious. So we can look at a command line and we can tokenize that, count rare tokens per host or per fleet. And we can be watching those types of things. Signed versus unsigned binary flags and publishers are important. Unsigned binaries, of course, might not even be allowed to execute. And that's something that we want to watch for, though, the attempted execution of unsigned binaries on a given endpoint. Privilege elevation, integrity level changes are also high-value signals. We can track the frequency of run as or service creation events per user and device. Here again, temporal context matters, the time frame matters. One-time elevation during an install window is probably fine, but a late-night elevation followed by unusual network connections is maybe not fine. Endpoint features are often highly predictive, but they require careful whitelisting for admin tools And they also require us to build allow lists for IT change windows in order to reduce noise. Let's turn then to aggregation. We can look at aggregation features and turn streams into profiles. We can compute per host and per user aggregates. And that helps to provide some unique counts per destination aggregates and so on. Things that are bursty in nature, that burst often, help us to capture how concentrated events are within a window. Uniform rate of request looks different than spikes of activity. And making sure that we are correlating things for beacon detection is also important within this context. We want to compare the behaviors that we have to baselines. A global z-score, how unusual is this compared to everyone else? Helps us to find outliers within our devices. We might even have a personal z-score. How unusual is this host compared to its own past behavior on this host? Helps us to catch some subtle drifts that global measures might miss. It also helps us to detect insider threats or compromised accounts if we have personal baselines there within this context. Helps, though, to keep those baselines time-boxed in order to adapt to legitimate changes in how software works or how people perform their jobs. I'm going to wrap up this lecture right where it is then. We talked about features here in this lecture, and features are what we use to make the behavior visible. That's all the data points that we collect that are useful. We collect that data, and we also create features as we're going forward because we have data that we collect, say the number of failed logins. Well, we create the value that is the number of failed logins by counting it. That's a feature that we want to watch as being potentially important in a cybersecurity AI context. And in order to get there, we need to build pipelines. We build that pipeline by producing a reproducible content, and we want to gather that data and be able to feed it through the pipeline in order to get clean data on the other side that we can then use to train our eventual models as we're building AI. So those clean pipelines are very important in the context of building AI for cybersecurity or really for AI for any context. So we'll continue and talk more about labeling and some other strategies and factors involved in creating AI for cybersecurity and beyond in a future lecture. Thanks for watching.